Okay, now we're just going to look at some different theorems with inversion and see what they do. So first of all, an inversion is not an isometry. It does not preserve distances. But it turns out we can actually prove that it's a continuous function. We're not going to do that in this class, but we can prove using real analysis techniques that this is a continuous function, which means it preserves neighborhoods, which means things that are close to each other stay, in quotes, close to each other with the way that we define that. It doesn't send triangles to similar triangles exactly in all cases. It kind of shuffles the points around a little bit as we read this theorem here. Let O be the center of an inversion whose radius is r, so we've got this inversion centered at O, radius of r. If P and Q are distinct points that are not both collinear with O, so they don't all lie on a line together with the center of the circle, so that P prime and Q prime are not going to lie on that same line, and P prime and Q prime are the inverses, then it turns out triangle OPQ is similar to triangle OQ prime P prime. Now if you look at that, it's not the original triangle in the same order. Q and P are actually shuffled around a little bit. So it swaps the angles. It doesn't preserve angles directly. It kind of shuffles them around, which is kind of strange. But let's look at a proof that actually does that. I guess really I'm going to show you just more of an outline of the proof idea here with the picture of what's going on. So we have O, which is the center of the circle, and it has a certain radius that I have said. I have the circle actually hidden, but we have this inversion by a certain factor of r. Circle has a radius of r centered at O. So Q and P are not on the same line as each other with respect to O. They're on two different lines, so they make a triangle. So with this dilation in this picture, it looks like they're both inside, and so Q prime's going out here and P prime's going out here. Okay. So if we look, this triangle OQP turns out it's not similar to OQ prime P prime. You actually have to flip it over. Okay. So by definition of the dilation, r squared is equal to OP times OP prime and OQ times OQ prime. That's the definition of dilation. Here's the transformation. Remember, we can show things are similar if we can come up with a similarity transformation that maps the one triangle onto the other. Here's the one that'll actually do it, and I'll just show you the picture of it happening here, okay, which will prove that the triangles are similar when we see that O goes to O, P goes to Q prime, and Q goes to P prime. It actually shuffles where P and Q go. So what we need to do is do the composition of the dilation or homothety centered at O with a radius or a scale factor of K, where K is defined this way to be OQ prime over OP. That's what we're going to need for everything to line up right. And then we're going to have to reflect across the line. That's the angle bisector there. We'll have to reflect across that line. So here's a picture of it. There's the dilation to increase the size. And there's the reflection, which went right on top of it. Okay. Again, there's a few details to work out to prove that the points go where they should, but there's a visual demonstration that that's what happens. Okay. So if we dilate, it's the same size, but it doesn't line up right. We actually have to flip it over. So Q and P have to be flipped. Okay. So triangle OPQ is similar to OQ prime P prime. So angles are not preserved directly. The angles in the triangle that we just looked at stay the same, but they're shuffled around. The angle at Q goes to P prime, the angle at P goes to P prime. So angles are not preserved, definitely not in the same order. And of course these points had to lie in a certain way anyway to even talk about that triangle. But it does turn out angles aren't preserved directly the way we just talked about, but the measure of angles between curves is preserved as invariant, which seems kind of weird. If it doesn't work for the triangles, why does it work for curves? Well, let's look at it in GeoGebra. Okay, so keep in mind that theorem we just talked about applied to very special triangles where the 2 points were not on the same line as each other with O, and O was one of the points on the triangle, was a vertex of the triangle. We're going to look at a couple of triangles here that wind up having the same angles, but they're not those types of triangles that we just talked about. Keep that in mind. So we're claiming these I actually applied. I've built some tools that will do inversion, and I've applied those to these pictures here, and it's kind of hard to make curves in GeoGebra, but I've set up, these are arcs of circles. And I've actually done the inversion, and it turns out this angle is the same as this angle, and the vertical angles are congruent to each other there. So Here's why, again with some of the details of the proof omitted, but we can make a line crossing all of these curves, which we can find points Q and R when it crosses this curve, and their images under the dilation R prime and Q prime will be here on the other curve. They actually, where the center of the circle is and the radius and everything, get reversed in this picture when you look at it. But those are the actual images I used an inversion tool that I built to do it. Now we can define these little triangles in here, P, Q, R, P prime, Q prime, R prime. Turns out that those are similar. Okay, the triangle, well, these triangles we know are similar by a previous theorem. OPQ, OPQ, the one with these two black sides and the red side is similar to O, P prime, Q prime, the other one with the red side. Of course, you have to flip them over like our other proof, but those are similar. And the other ones with the green side are similar to each other. Pretty obvious there with the green one. You see if you stretched it, you'd have to flip it over. Okay. So those triangles, those two sets of triangles are similar. That will allow you with some work. Now this takes a little bit of work and I'm not going to show it here, but using those two sets of triangles that we have and these third sets of triangles that are inside, you can use some subtraction and the right combinations and actually show that these two angles at P and P prime are the same as each other. I've got them measured with GeoGebra and we can see that they are, but we can actually prove that using the angles in the similar triangles up here. It's not immediate, but you have to go through the algebra on it, but it works out that it is true. And that's actually what we need to show. If I add entire lines, we measure the angles between curves with tangent lines. Those are actually secant lines, but I can move the points closer and closer to each other and I'll eventually get to the tangent lines, which would be the angles between the curves. Remember, it's very important that these are continuous transformations, but inversions are continuous.